So today we're going to be going through an Astro challenge paper. I've got Sophia here, who's
Hello.
going to help out. You do physics at university, don't you?
Yes, just finished my second year.
So she is much better than me at actually explaining this stuff. So we're going to go through the Astro challenge paper, first of all. We're not going to do every question, but yeah, do you want to just explain a bit about the structure of this paper?
So the Astro challenge paper is sat in autumn term of Year 13 in general, but if you're younger, then you can choose to sit the paper as well. So the way the Astro challenge paper is structured is, so we have section A, that'll be about 10 multiple choice questions, 1 mark each. Section B will have 2 short questions, about 5 marks each, I think. And then section C will have 2 long questions. But in section C, you choose only one of those long questions and you attempt them. And in the other sections, you do as much as you can.
Cool. So I thought today what we do is, rather than doing every single question, we'll just do a couple of each. So we'll maybe have a look at some of the multiple choice, maybe one of them from section B and one from section C. You've kind of worked through this already. I've looked at the questions as well and how to go at them, and actually they're really interesting. I think a lot of them are based on what you probably currently know about A-level physics, but there's also extra information. So let's begin, shall we, with number 3.
Yeah. It's worth saying that one of the main differences between the Astro Olympiads that are part of the BAAO and the Physics Olympiads that are sort of the physics branch of the British Physics Olympiad is that in the Astro papers, you will occasionally have to self-study some things that you may not have covered in A-level already. A lot of it will simply be building on what you already know in A-level, and most of the questions will only require A-level knowledge. However, there are a few things that is worth reading up on, and there's loads of resources that you can use to do that on the BAAO website, which I'm sure Lewis can direct you to.
Yeah, so these ones here, the first one is a bit of a self-study guide for the astrophysics, written by the legendary Alex, who basically has done a huge amount for the
He's
Olympiad.
awesome.
Yeah, and also a super nice guy. So if you're watching this, Alex, hello.
Hi.
But yeah, so basically you can learn a bit more about ellipses, you can learn more about things like the parsec, apparent and absolute magnitude. Actually, a lot of things come up for maybe people doing the astrophysics option for AQA, or bits of the Astro stuff that you might learn towards the end of Year 13.
If you do already happen to have the AQA textbook that has the astrophysics content in it and your school doesn't cover that, then a good place to start for self-studying some of the astrophysics concepts that might be useful for these Olympiads is to go and have a look at that content from the AQA astrophysics option, because it covers things like magnitudes, and it will probably explain them quite well. So.
Yeah, and there's this other thing here. This is a really good document that's been really well written and put together. This is something I think different to A-level physics. It's more about the observational astronomy, so things like the constellations, things about the stars, and how you can maybe work out the time of year or latitude and longitude. And so I think, again, this one here has lots of useful information, which is a bit different to A-level physics, but really important to look at before you have a go at these questions.
Yeah. Another big difference between the Astro and Physics Olympiads is that the Astronomy and Astrophysics Olympiads are, well, as the name says, it's not just astrophysics. There is some observational astronomy as well. In the Astro Challenge, there will be a few questions that might ask you sort of, what constellation is this star in? What's this constellation based on pictures? And everything that you do need to know is sort of clearly listed in the syllabus and in the self-study guides. So do just have a look at those. We try to introduce it sort of a bit at a time so that there isn't an overwhelming amount of stuff that you need to self-study.
But it's also really interesting, actually. It's kind of interesting stuff to study. So let's have a look at number 3 then, shall we? So yeah, there you go. Okay, do you want to go through this question and how you'd approach something similar? So
I'm tempted to do this. It's so funny with the big sheet. It's worth saying that even though we say you'll need to self-study a few things, all the equations that you'll need are in almost all of the equations that you'll need that we think aren't covered in A-level syllabuses will be in the important formulae page at the beginning of each paper. So definitely have a look at this page and see what's there, and make sure that you know what each equation is and when you might want to use it.
Cool.
Reading this question, they've said, here's the supernova. Its apparent magnitude is 10.8. Its distance away is 21 million light years away. And they've asked, what's the absolute magnitude? It may seem like there's a lot of extra things that you need to learn, But if you have a look at the important formulae page, that is pretty much the vast majority of what new concepts might come up. Yeah, just have a look at those equations, know what they're about. The self-study document goes through things in quite a bit of detail with worked examples. As a bit of background, a magnitude is a number that denotes how bright an object is in the sky. The apparent magnitude of an object denotes how bright it is as seen from Earth. So if you see a star in the night sky, its apparent magnitude will tell you how bright it looks to you. But apparent magnitudes aren't always completely useful, because sometimes we want to compare how bright objects are intrinsically and not worry about how far they are away. For that we use absolute magnitudes. And the absolute magnitude of an object is simply what the apparent magnitude would be if the object was 10 parsecs away.
And they've all got a number, haven't they?
Yeah.
And the more negative the number, then the brighter it is, which is
Yes.
kind of not what you'd expect.
It's counterintuitive, but it's just one of those quirks.
Like a quirk of history, I suppose,
Yeah,
isn't
it's
it?
just a quirk. In the important formulae page, we have a formula that relates the apparent and absolute magnitudes of an object. I would be tempted to just use the first one and then rearrange it, which is an exercise that you could do in your own time, actually. These two formulae can be derived from one another. In particular, you can derive the second formula from the first one by substituting what the brightness of an object is in terms of its luminosity and its distance away. But that's for your own time. I'm going to outline in blue all the formulae that are given in the important formulae section, just so that you're aware which ones you don't need to memorize. So in this formula, this lowercase m denotes the apparent magnitude of an object, the capital M denotes the absolute magnitude of an object, and this d here is the distance of the object away in parsecs. And this 10 here denotes the 10 parsec distance away that we're setting as a kind of reference to measure absolute magnitudes. So what we want to do is we want to rearrange this for the absolute magnitude of the supernova. You'll notice that I've added in this 10 here just to clarify that the log is base 10. I'd recommend just adding that for clarity, but you don't have to, because magnitude formulae will always be base 10 anyway. Cool, and now we can put some numbers in, but hang on. In order to substitute in the distance of the object, we have to use the distance in units of parsecs. That's the requirement for using this formula. However, we've been given the distance in light years. We've been told it's 21 million light years away. So let's break this down. So 1 light year is, in meters, the speed of light in meters per second times the number of seconds in a year. And let's put some numbers in this.
I must say, you have beautiful handwriting.
Thanks.
It's so clear, it's like makes mine look really messy. So
No.
yeah, the pens help as well, don't they?
Yeah, I love
Like
these pens so
the
much.
famous physics pens.
Yeah. And the number of seconds in a year, I'm going to use 365.25 as the number of days in a year. Each day has 24 hours, and each hour has 60 minutes, and each minute has 60 seconds. Some people go ahead and memorize the number of seconds in a year. I don't feel that's entirely necessary. I just kind of multiply all those numbers together each time. So that's the number of meters in a light year. I'll just put that unit in there. But we want to know how many parsecs there are in 21 million light years. This is just there for a bit of context about how far a light year really is. Having a look at the constants sheet, we've been told that 1 parsec is 3.09 times 10 to the 16 meters. So, how many parsecs are there in 21 million light years? Well, first let's write down 21 million light years in meters and then divide it by the number of meters in 1 parsec. So 21 million. Right, let's put this in our calculator. So 6.43 times 10 to the 6. So now we have the distance of our object away in parsecs. So now we can happily substitute everything into this formula to get the absolute magnitude. I was just saying, I would have done this all in one go and just done the unit conversions inside the formula, but we're just showing it step by step for now. I'm using subscript Sn to denote the supernova. Its apparent magnitude was 10.8, and we want to subtract 5 log 10
Okay, we've gone from my calculator. We're going back to your calculator. We've got our different settings. We've got our own personal preferences, don't we? But I've just done the calculation, and it's minus 18.24. So a really negative number. But what does that tell us about the object?
It's pretty bright.
Pretty bright, yeah, being a supernova. Okay, and I guess then the actual answer is, I guess you've got to choose A, B, C, or D, like any kind of multiple choice thing. So the answer for that is A.
Yes.
That's a lot of work for 1 mark, isn't it?
Yeah. Some of these multiple choice questions will take you more than 1 mark's worth of time. However, some of them will take you a lot less, especially the observational astronomy ones. Those can be pretty quick. So I would say don't be thrown if it's taking you too long. Definitely use your time wisely and come back to it at the end, because some of the longer questions might get you more marks per minute than some of the multiple choice questions. But most of all, just persevere and don't be thrown if it's taking you longer than you think it should, because in Olympiads, you are going to have to do a bit more for each mark than you would in school.
So we've got 1 mark then. Now let's have a look at question number 4. Again, this one here is about something recently that's happened in space in terms of like rovers and things. But also a lot of it is kind of relying on like your normal kind of general physics skills about intensity and area and power and things like that. So again, if you could go through question 4, that'd be awesome.
Can I read it?
Yeah, of course, yeah, sorry, yeah. We'll put it up on the screen as well, so you can always see the question.
This one's quite a wordy one, so I thought I might illustrate like how you can extract information from it. So this question says, so in August 2023, India became the 4th country to successfully land a spacecraft on the moon. The Chandrayaan-3 mission also involved the Pragyan rover, which was fully dependent on its small solar panel to provide it with the 50 watts necessary to move around the lunar surface and do experiments. Assuming it was pointing at the sun the whole time, what was the minimum solar panel area needed? So this question's a bit long in terms of the actual preamble, but I would say there are 3 key bits of information from this. So we know that the power we want is 50 watts. That's the power we need to power this thing. The other piece of information is that we're on the moon. I'm going to write that down. And then the other bit of information, I mean, one of the most important things you need to extract from reading any question is, what do they actually want you to do? And what they're asking is, what's the minimum solar panel area needed? I'm going to use P to denote the power that we need to power this spacecraft, and A is the area of the solar panels that we're going to need to provide that power.
So I think that's really important. It's just like, there's lots of text. To be honest, the fact, the name, the dates, that's not really so important to solving the question. It's like 50 watts, it's on the moon, what's the area? And it's just trying to take, actually extract the useful information from that question to actually work out what we need to do. So that's, again, like just, good exam technique for anybody doing any exams, not just these
In any
papers.
exam, I'd recommend, as you read the question, just write down the key things that you need to remember from it, and then you're not sort of going back through and trying to extract important things like 50 watts from things that are less relevant to answering the question, like August 2023.
Okay, so what next? What would be your first stage in something like this?
We've got power, we've got area. So the natural question to ask would be, well, what's the solar power per unit area that we're actually going to receive when they're on the moon? And they've helpfully said that you can assume that this solar panel is always pointing at the sun. Let's draw a diagram.
I think diagrams are super important, aren't they? It's like, because I think, again, a lot of the questions here, it's quite difficult sometimes to work out what they're asking you. But when you draw the diagram, you go, okay, it's this distance, this far away. And it's just, good kind of practice for any kind of physics exams you're going to do in the future.
Yeah, some of your diagrams will be really helpful. Some of them will be less helpful. This might be of the slightly less helpful kind. But the reason I drew this was firstly to say, generally in astronomy and astrophysics, if you write a circle with a cross in it, almost always people will interpret that as meaning the Earth. The moon I just did as a dot, and then I did an arrow to the sun. The distance between the Earth and the moon is so much less than the distance between the Earth and the sun that for the purpose of this calculation we say, well, let's say that the distance from the sun to the moon is the same as the distance from the sun to the Earth. That way we know how far away this rover is from the sun, and hence we can use that to figure out what the intensity of sunlight will be on the moon. So we're interested in what the power per unit area will be on this rover. Let's call that quantity S. Sometimes S is used to denote the solar constant, which is the intensity of sunlight, i.e. the power per unit area of sunlight on the Earth. We're going to use S is the power per unit area. The power per unit area is going to be equal to the luminosity of the sun divided by 4 pi times the distance from the sun squared. In astronomy and astrophysics, writing a circle with a dot inside of it almost always denotes the sun. It's just kind of a standard notation. Okay, but what's the distance of the moon from the sun? Well, we've said that that's going to be almost exactly the same as the distance of the Earth from the sun. And we can go to the constants sheet to write that down. From things like the syllabus and the self-study guide, you may know that the distance of the Earth from the sun is 1 astronomical unit. 1 astronomical unit is 1.5 times 10 to the 11 meters, and you're given this in the constants sheet. You're also given the luminosity of the sun. So we know S if we were to substitute these in. What we really want is A, though. We broke down the previous question to a few steps. What I'd usually recommend doing is to substitute in symbolic formulae, rearrange, and then put in your numerical values. So what we're going to do is, we know that S equals P over A. So what we really want is the area, which is P over S. But we also know that S is equal to this formula here. So let's substitute that in. We've substituted that in, and we've been given the power, that's 50 watts, that's the power we want. We know that the distance away is 1.5 times 10 to the 11 meters, and we also know the luminosity of the sun. So we can go ahead and put those values in now.
And this time you're back to your
my
calculator.
own calculator. So you can see the fractions.
And that's a calculator you're using at university for physics?
Yes.
So just a standard scientific calculator?
This is my day-to-day calculator. I got it while I was doing A-levels. Yes, and it's just still serving me. So we're getting an area like this. This is the area in meters squared. We want to convert this to centimeters squared, but actually we don't even need to do that because we know that it's going to be this times some multiple of 10 in any case, and the only value that it could be is B, 370 centimeters squared.
Cool. So again, a lot of work for 1 mark, but I guess the more you do this, the quicker it becomes.
Yeah, definitely.
Yeah. So this is looking at lots of text in the question, identifying the key numbers which are important, looking at the constants, which I think, again, some of these are you probably will be familiar with from normal A-level physics, but there's probably some new ones like the luminosity of the sun. Mm-hmm. And after that, it's just like the way you'd approach any other physics problem.
Yeah. A good tip for these exams is to detach the page with the constants sheet and even the formula page as well, and just have it next to you, and then have the questions on like the other part that you've detached it from, to save you having to sort of flick back and forth, because that's allowed. I don't see why it wouldn't be allowed. You can detach the staples all you wish,
so
if that makes it more convenient.
To kind of save you those
Life
few minutes. So now let's have a look at a few more questions from the observational astronomy part of the paper. Right then, so here we have question number 6. Now this one, I believe that if you haven't studied like the course material, it's very hard to know that just off the top of your head, isn't it?
It's also so different to sort of a more physicsy question. You might feel really thrown if you haven't met these kinds of questions before. But especially for these multiple choice observational astronomy questions, it's really helpful and quite important to know what you need to know, not just knowing it in the first place.
Yeah, and I think this is where this guide in particular that you wrote.
Yep.
Yeah, so basically you've put this together, haven't you? And there's a huge amount of information in here, and this is based on the syllabus. Sorry, I've got, again, lots of paperwork.
Yeah.
And it's syllabus, again, you can find on the website. And this has lots of information about what exactly you need to know about. So I think it's somewhere over here, isn't it, that it mentions about what you need to be able to recognise in terms of different objects?
So this booklet here goes through all of these syllabus points in a bit more detail. Some of these things are simply stars, constellations, asterisms, deep sky objects that you might need to simply remember. We've tried to make it so that there's not too much, but also that there's enough that it feels, there's a bit of a challenge to make sure you know them.
So this question is about this, is it Messier number?
Yeah.
So,
well, technically Messier, I think, but
Messier. Okay.
I say Messier.
Okay, apologies about my pronunciation.
Charles Messier was French, so.
Okay, and this is kind of what you wrote in the guide, isn't it, about some of the deep sky objects?
Yeah, so the things you need to know for each deep sky object is which constellation it's in. For the Astro challenge, you don't need to be able to label anything. We won't give you a star map, we won't ask you to label anything on a map, but simply you need to remember which constellation each one is in. And you also need to know what type of object each one is, and finally being able to recognize a photograph of each one. And this seems a bit daunting, but there are only 4 objects that you need to remember these things for. We've got the Crab Nebula, the Orion Nebula, the Andromeda Galaxy, and the Pleiades. And each one has its own Messier number. I should say a bit of context, which I think I also wrote in this guide, is that the Messier objects are a catalogue of 110 deep sky objects, which simply means interesting stuff you can point your telescope at if you've got the time.
But you don't need to remember 110 of them.
But you don't need to remember 110. If you go to the international competition one day, you might know all 110 Messier objects, but for the Astro Challenge, we've asked you to know 4.
And do you know all 110?
I don't know all 110.
But you did the international, didn't you?
I did the international competition. I did well. I didn't know all 110. I knew quite a few of them.
How well did you do?
I got a bronze medal in the international competition.
Fantastic. And that's like against like people all around the world, isn't it? So that's pretty incredible.
Yeah, but
very, very understated here. Okay, so we've got some deep sky objects. Looking at the question now, I mean, I can see, especially with the guidance next to me, that picture looks like that one.
Yes. So in the international competition, recognizing the photos is actually a skill that you're recommended to have. And the nice thing is that they'll generally only use the most common image of it that you can find, generally the first one that you see on Wikipedia. So when you see these photos in the study guide, we won't give you the same object but like a different photo. We will be giving you that photo if we want you to recognize that object.
So looking at this then, as somebody who's maybe not a specialist in this area, I would say that this looks like the Pleiades, M45, so I would say the answer is D.
Yes. As I said, it's helpful to know what you need to know. When you look at this, if you remember that the 4 objects that you need to know are M1, M42, M31, and M45, then immediately you can rule out M43 and M44, which are options B and C, because we probably won't be cruel. We won't be asking you to recognize an object that we haven't told you about in the syllabus. So your 2 options are M42 and M45. Even if you don't remember what constellations they're in, you might remember that M42 is a nebula and that M45 is an open cluster. And I'm not sure, Lewis, this looks more like a cluster of stars to me than a nebula, which would be just more of like a cloud. So even if you don't remember all the information, you can kind of use the information that you do remember to eliminate certain answers.
And I think for this one here, it's a 1-mark question, but it doesn't necessarily take you 5 minutes of kind of big calculations. This one here, if you've done your revision beforehand, using the resources which you've put together, then actually you can get that. You might just almost know it instantly if you've kind of done lots of stuff. So that 1 mark might take you 10 seconds to actually work through.
These are questions where you save time for the 1 markers, which take you longer than 1 mark's worth of time.
Cool. And so the next one then, number 7. Which of the following stars is in the constellation Taurus? So I must say again, this is something that I didn't know before I actually had a look at this paper. But looking at the syllabus, it's mentioned, isn't it?
So on the Astro Challenge observational syllabus, there are 8 stars whose constellations you might be expected to recall. And Aldebaran, Castor, Rigel, and Sirius are all on that observational syllabus. So we can't immediately rule some out and say, oh, I don't recognize the name. That's probably not one that we were asked to know. All of these could be the one, all these could be the answer. But again, if you've done your revision, you'll know that Aldebaran is the only one from this list that is in Taurus.
Cool. So 7A, easy marks, isn't it?
It may seem like a lot of information, but if you make 8 flashcards and look at them a few times, you'll know the 8 stars. So yeah, hopefully, and then doing that, learning observational astronomy in sort of small chunks, you can start to build a much bigger knowledge, which can be quite fun to impress people with when you go out at night and it's like, oh yes, that's Arcturus or whatever.
Fair enough, yeah. Or you could make it up if they don't know anything about space,
Yeah,
so
yeah.
they wouldn't know the difference.
Yeah.
Okay, right. So the next one is question 8. This one is about some constellations. I've seen again in the guide, it has about, I think, 8 constellations that you need to know about.
So the syllabus has 8 constellations, 3 asterisms, 8 stars, 4 Messier objects.
So what's an asterism?
An asterism is a group of stars that look like they have a very recognizable shape, but themselves they don't form a constellation. So the first asterism that's mentioned is the Big Dipper, which you might already know how to recognize. And the Big Dipper is not itself a constellation. The Big Dipper is part of a bigger constellation called Ursa Major. But the Big Dipper is an asterism that forms a recognizable part of a constellation. They can also combine different constellations. For example, the Great Square of Pegasus has 3 stars from the constellation Pegasus, but 1 from the constellation Andromeda.
Okay, so again, huge amounts of really interesting information actually. And for this one, once you know that there are 8 different constellations to learn, you can find a map of it and you can sort of see what the pictures look like. And then I guess you can then start to identify what each one of these are. But the question says, which has the nearest comparable sized galaxy to the Milky Way? So which galaxy is that?
The nearest comparable sized galaxy to the Milky Way is the Andromeda galaxy.
Yeah. So for question 8 then, the nearest comparable sized galaxy is Andromeda, and that's why it's going to be D. So that one there, again, if you know the kind of a bit of the background, then you can get quite a few marks quite quickly.
But also by knowing what you need to know.
Yeah.
Not just knowing the things themselves.
Exactly, yeah. Okay, so section 1, multiple choice, and then you go on to section B, don't you? So this one, there's 2 questions you do. Each is worth about 5 marks. I reckon we should have a look at this one first of all. So we might not necessarily read out the whole thing. We'll put it up on the screen so you can read it. But again, I think it's a question where there's some really interesting context, and actually it's about something that is kind of being developed, and I didn't know anything about this, to be honest, until I saw this in the paper.
It seems quite interesting.
Yeah. So what would be your approach to this question then?
So first of all, as with any wordy question, I'd go through and I'd make sure to write down just the key bits of information so that I can refer to that list of information that I've just written down, rather than referring back to that paragraph there.
Cool.
That's going to speed up my working for the rest of the question. So we won't read it all out, but looking through this, we know it's going to allow satellites up to 200 kilograms to be put into orbit. So let's say mass of satellite is going to be lowercase m, and that's going to be 200 kilograms. The payload is accelerated in a 45-meter radius circle. That seems relevant. Let's denote the radius of that circle as just capital R, until it reaches about 1/5 escape velocity. So until it reaches that velocity, we're saying that the final velocity of the satellite in this launcher is going to be 1/5 of their escape velocity. I'm going to denote the final velocity as VF, and I'm going to say that's 1/5 v(esc) for escape velocity.
Okay.
At 60 kilometers altitude, it's going to be accelerated further and end up in orbit. That could be relevant. So let's denote that H and write that down. So now let's move on to what we're actually being asked here. Part A. Show that the satellites launched in the orbital launcher must be able to endure centripetal accelerations of up to 10 to the 4 g.
Okay, so this looks really interesting. So basically you've got like something where something is spun around in a circular path, and then as it gets up to the right speed, I guess, or velocity, it then shoots out this kind of thing up here, and it just gets sort of like shot off into space from ground level, which sounds incredible.
It's quite funny to imagine.
Yeah, and I can imagine actually if something was going around, you know, a 45-meter radius loop, that's like almost 100 meters in diameter, and it must be going incredibly fast. I guess it'd be quite scary to see it actually go off. So the first one then, it's a show that question. So they've given you the answer, which is always quite nice in like a kind of question like this. But we need to look at the centripetal acceleration. So what would be your approach to this?
So what is centripetal acceleration? It's the acceleration towards the centre that you require for an object to move in a circle of a given radius. Considering this question is asking us to find some centripetal accelerations, let's write down the formula for centripetal acceleration. So we have two forms of this formula. We have AC is omega squared r, and A subscript C is V squared over r. So what information have we actually been given? Upon reading the question, it's quite wordy, but we know that when it's released, its final velocity is 1/5 escape velocity, and we've denoted that Vf here. So it seems like we're going to be using the V squared over r version of this formula for centripetal acceleration. Actually, it's going to need to be able to endure centripetal accelerations of Vf squared over r. In this case, r is the radius of the circle around which it's moving, which will be the 45-meter radius circle of the launcher. About the final velocity, we've been told that it's 1/5 of the escape velocity. So let's substitute that in so it's in terms of things that we actually know from the question. But hang on, what's escape velocity?
I was just going to say that. So we're talking about something needs to be travelling fast enough to escape, effectively the Earth's gravitational pull. And if it's not going fast enough, it's just going to come back into Earth, isn't it?
So, escape velocity interlude.
And again, I think if you're doing A-level physics in year 13, you'll probably be quite familiar with this, or you might have had to work it out beforehand.
Yes. We'll go through the derivation quickly, just so that everyone's on the same page.
Yep.
So, the escape velocity of an object is the velocity that you need an object to have in order for it to be able to reach a point an infinite distance away from where you're launching it from, without coming back down. The way I like to think about this is in terms of the kinetic and potential energy of the object. You want this object that you've launched to have enough kinetic energy that it completely just overcomes the gravitational potential energy that it has. In other words, you want this object to have enough kinetic energy that it gets out of the gravitational field of the object, as such.
Yeah.
And that's the point at which the gravitational potential energy will be zero. The quick way to think about this is to set the total energy as equal to zero. So the total energy of an object in a gravitational field around some other object, for example, the satellite around the Earth, will be, just to be clear, this here is supposed to be a circle with a cross inside it as the symbol that denotes the Earth. And this is the total energy of the satellite in the Earth's gravitational field. You'll know from A-level, this is your formula here for gravitational potential energy. This is your formula for kinetic energy. Add them together, and we know that we want this object to have enough kinetic energy to get over the gravitational potential as such.
Yeah, and that's when, effectively, it's so far away from the Earth that the potential energy is zero. So energy is like a negative thing. Okay, I'm explaining this badly, but basically, the gravitational potential energy is negative, and you want it to be increased so much that it comes to zero.
Yes.
Yeah, cool.
And in order to do that, you need your kinetic energy to match that.
Yeah.
Remember, the escape velocity is the border case between being able to get to infinity with some kinetic energy left over and not being able to reach infinity at all. That's why we're setting it to zero. So when you set it equal to zero and rearrange, you get that. You end up seeing that these need to be equal to each other, as we discussed. That might be a more intuitive way of seeing this. And so when you rearrange this for the escape velocity, you get this.
So looking at that formula there, we need to know the radius of the Earth and the mass of the Earth, which are given to us in the important constants. So that means we can actually then work out the size of that escape velocity.
Going back to what we were initially planning to do, by the way, I should add, here we've derived escape velocity, but if you remember this formula off the top of your head, having practiced some of these, then it's fine for you to just go ahead and use that there. But equally, if you don't remember the formula, then this is how you can quickly derive it. So going back to what we were initially being asked to do, we want to find the centripetal acceleration of this object in the spin launcher. So going back to this equation that we wrote down here, we know that the centripetal acceleration is 1/25 times escape velocity squared over r. But warning, this r here is not the same as this r here. Be careful not to make that mistake. That's why I've added the Earth symbol here. So r without any subscript here is the spin launcher radius, and r with the Earth symbol as a subscript is the Earth's radius. We're going to substitute in this formula now, and we're going to get, I write things slightly illogically sometimes.
No, that makes sense to me.
Okay,
You
cool.
basically, just combined all of these things into life. And I think this is a really nice thing to like do your rearrangement, and then you just have one step where you put the numbers in rather than having lots of intermediate calculation throughout.
Yeah.
I think that's really good practice, isn't it?
Sometimes it can be useful to get intermediate values in terms of the markers checking that you've got
Oh, okay.
Sometimes you can get marks for intermediate values. However, if you get the correct thing symbolically, you'll get those intermediate marks anyway. And I would generally recommend for speed to sort of get everything symbolically, rearrange, and then put your values in.
Okay, and I guess we know the value of G. It's just the gravitational constant. We've got M, the mass of the Earth, which is here.
Okay, let's put the numbers in.
Okay, let's do that then.
All right, G, I believe, is 6.67 times 10 to the minus 11. And our result is kind of promising because the question has asked us to show that the satellites must be able to endure centripetal accelerations of about 10,000 times G. Putting our numbers in, we've got about 1.11 times 10 to the 5 meters per second squared as our acceleration. But they've asked us to show that it's about 10 to the 4 G. So dividing this by 9.81 gives us the centripetal acceleration in units of G. And it comes out to be 1.13 times 10 to the 4 G, which is wonderful because that's around about 10 to the 4 G as required.
Yeah, and I think it's always nice when you have a show me question and you get the answer that you're trying to show. So that kind of gives you a bit of confidence.
In a show that question, make sure that you put in the numerical values and give your answer to at least 3 significant figures, because that way you can get all the marks for it.
Fantastic. So that's the first part, and now we're going to look at the second part.
Yes.
So we've got the answer to part A. Now part B, I guess even if you didn't do the first bit, you've been given a number that's going to be useful. So for the second part, we just need to look at the minimum number of revolutions per second required to release a rocket. So what's your approach to this?
So my approach to this was, we can go back to the 2 versions of the formula for centripetal acceleration that we wrote down earlier. We know that centripetal acceleration is omega squared r, and it's equal to v squared over r. And whilst for part A we used a equals v squared over r, for this part we can use a equals omega squared r. That's because we know that omega is 2 pi f. I think this comes up in circular motion in A level. And so we have these 2 things, and so we can write the centripetal acceleration in terms of the frequency in hertz rather than in terms of the angular frequency. We substituted in omega equals 2 pi f into a equals omega squared r, and then we rearrange for f, which is a frequency in hertz, and substitute our numbers in. So this one is, I think, easier conceptually than part A.
I think so, yeah. And I think if you've got part A, you're probably going to get part B, aren't you? And again, this is just kind of normal A-level physics that you're using there. So the answer is about 7.9 hertz, which is, I think, frighteningly fast. Like if you imagine, like a 100-meter diameter kind of ring with something spinning around it, and if that satellite is going around 8 times a second.
Yeah, that entire ring, 8 times a second.
Yeah, and then it gets flung off into space. But again, I didn't know about this, and I thought this was a really interesting question.
Yeah.
So part B, the short answer up to about 5 marks, and there's 2 questions to do. And then I guess the finale is section C, isn't it?
Section C. So at first glance, this question looks quite intimidating. There's lots of words, some of which you may not know the meaning of. This is all part of what makes Olympiads harder than just school. They will give you lots of information. They will mention lots of words that you don't know the meaning of, but that's okay.
And again, this looks completely different to a normal exam style question. Like the difficulty is a lot harder, and there's just more information to kind of actually take in. So any marks that you're getting show that you're doing incredibly well, because there aren't easy marks to gain on the paper. So yeah, let's see how you did this one here. So
yeah, part of the trick to doing well in these ones is to sort of remain courageous and resilient and don't let it throw you too much, because in a sense, it's easier than you think from just looking at all the information there.
Okay.
This one slightly reminded me of some of the data analysis questions that you might get in the International Olympiad, because you've got a graph, you're extracting some data from it, then you're using that data to work out some of the things. All right, let's get into it. So as I mentioned, the first thing I did was I went through and I wrote down the values that we've been given in this preamble here. I've written Zi for the initially measured redshift, and then Z for the new, more precise redshift. And I kind of noticed sort of, why would they give you this value of the redshift if they've also measured it more precisely later? But, oh well, maybe there's a reason. I wrote down them both.
Okay.
But from reading that first paragraph there, you can see that these are both the redshifts of the galaxy, but the second one is just has been measured more precisely since they made that first measurement.
Yeah.
They've given you the luminosity distance of the galaxy, and if you don't know what that is, that's okay. Don't worry about that for now. Just plow on with the question.
Yeah.
It will be okay. So then we look at the rest of the preamble, and there's no values here that we need to extract out. Okay, so we can move on to reading part A. Realistically, you will have missed some things from the preamble, so you may need to go back and read it later. That's fine, as long as you've got your values written down. So part A says, astronomers are normally interested in the continual UV flux at around 150 nanometers in the emitted frame to work out the SFR. You read that and you're like, hang on, what's the SFR? So you go back to the preamble for a second, and here it says that SFR is the star formation rate. Cool. By considering the shape of the continuum from rest frame to 140 to 160 nanometers, measure the spectral flux density from the graph at emitted wavelength 150 nanometers, and hence show that the absolute magnitude of this galaxy at that wavelength is between -22 and -21.
So there's a lot of information
Yeah.
there, but actually I think some of that is just information about how they actually got the measurements, you know, the difference between Hubble and the James Webb Space Telescope in terms of readings, and then some new information that nobody will have necessarily seen before. So what was your first approach?
What we want to do is go through this and pick out what they've told us to do. And the first real instruction here is measure the spectral flux density from the graph at lambda emit equals 150 nanometers. That's the first thing that they said, do this, work out this. So we say, okay, we go to the graph and we think, well, actually, they said measure the spectral flux density at emitted wavelength, 150 nanometers. But if we've measured a spectrum of something, the spectrum we record is not going to be showing the emitted wavelengths. It's going to be showing the observed wavelengths. So if you're familiar with the concept of redshift from things like the syllabus, the study guides from the website, or from school, you'll know that the wavelengths of things in galaxies that are moving quickly away from us will be shifted. They'll be longer. And you don't need to memorize the formula for redshift. It's in the formula sheet at the beginning of the paper. And the redshift is the difference between the observed and emitted wavelengths divided by the emitted wavelength. It's also equal to the recessional speed of the galaxy divided by the speed of light. But we won't need that for this question. This question, right now, what we want to immediately do is to convert this emitted wavelength of 150 nanometers to what wavelength would be observed. We know the emitted wavelength. We want to find the observed wavelength. We've been given the redshift of the galaxy. We've actually been given 2 redshifts of the galaxy, but the second one is more precise, so we're going to use that one in our calculations. This delta lambda here is the observed wavelength minus the emitted wavelength. It's that way around because when we're thinking about redshift, we know that the wavelengths are going to become longer as they're redshifted. So to keep this positive, we're subtracting the emitted wavelength from the observed wavelength. So we'll substitute that into our formula for redshift. And because it's the observed wavelength that we're trying to solve for, we'll rearrange this to get the observed wavelengths in terms of the emitted wavelength and the redshift. And then we can put our values in and get that observed wavelength. And going back to what we're actually trying to do here, the question said, measure the spectral flux density from the graph at lambda emit equals 150 nanometers. So what we've done now is we've figured out the observed wavelength, which is the value along the x-axis that we're going to have to find. I should also mention that if you were to not realize that this spectrum had observed wavelengths rather than emitted wavelengths along the x-axis, I think when I was initially thinking about this question, something I noticed is that, so here they've said 150 nanometers, And converting that to micrometers, which is the same as a micron, that's 0.15 microns. But this graph doesn't really show 0.15 microns. So that could be your first clue into that this x-axis is not the emitted wavelengths, but the observed wavelengths. I think that things like that will help to sort of guide you in sort of any conceptual steps that you might have to take. So we found the observed wavelength. They said measure the spectral flux density. So we go to this graph and we measure the spectral flux density. I mustn't mess this up. I'll need a ruler.
So this is one go.
Yeah. One take. I mean, I have a pencil, but it's more fun this way. Hang on. So when I did this question, I mean, you could probably be a bit approximate about it if you wanted to, but to make sure you're getting those 5 marks, it doesn't take too long to be precise. So this is 4.5 centimeters. Hang on, I'll need to like think about this.
Yeah, so this is
sure
printed out on A3 rather than A4, so that might not help.
Yeah, by the way, this is on A3.
Okay, so we want 4.5 centimeters, isn't it?
And we want to measure 1.74. That's about 1.74 is kind of like 1.75. So if you were to divide it into 4 parts, then you could do that.
Yeah, so it's about 3.3 centimeters from this end. So
it's about 3.3.
Yeah.
That's about there.
Yeah, that's about right.
And important thing to note, they have said by considering the shape of the continuum, not just the shape of the spectrum. And you might read this and think, what do they mean by that? At that point, you can go back to this preamble and scan through to see if they said anything about the continuum that you have missed. So here they've mentioned one of the advantages of a detailed spectrum is to try and determine the properties of the ultraviolet continuum. That is, the underlying shape of the spectrum, ignoring absorption and emission lines. So the key thing to note here is the continuum is the underlying shape of the spectrum. So we can kind of draw this on actually. The continuum is going to go something like this.
Yeah.
Not bad for one take.
That's pretty good, again.
Okay.
Yeah.
And so awesome. It's good that they've mentioned that, because otherwise we would have gone all the way up here, because there happens to be a little peak here. But we know that we're just considering the continuum. So we're just going to go up to here. And we're going to try and make this perpendicular.
And I guess in the marking there's going to be a fair margin of error for, you know, the fact that people have to actually take stuff off a graph as well, don't they?
There will be a fair margin of error. When I did this and read off the graph, I got that the spectral flux density, F lambda, 1.3 times 10 to the minus 20 ergs per second per centimeter squared per angstrom. And if you don't know what an erg is or what that entire unit means, that's okay. You've done what they asked.
I've only seen that once, and I've only seen that come up in a BAAO paper. So I've never seen this in anything outside like the Olympiad, but it doesn't matter, does it?
Yeah, that doesn't matter. There will be some quirky, goofy units that you may not have encountered before.
Yeah.
Same with words, that's okay, especially in the long questions at the end. If this is the question you've chosen, or like, if this is the question you've chosen as opposed to the other one, and like there's things that you don't know, just plow on. You will get many more marks than you think you've got. I can guarantee that, as long as you just remain resilient. Okay, moving on. We've got F lambda. We've done this first thing that they've asked. We've measured the spectral flux density. They've said measure the spectral flux density at the emitted wavelength of 150 nanometers, and hence show that the absolute magnitude of the galaxy is between minus 22 and minus 21. So we probably want to work out what the absolute magnitude is that corresponds to this spectral flux density that we've just measured. Like, how do you relate spectral flux density and absolute magnitude? This is not something that's immediately obvious, but then you look over the page and you see all these helpful formulae that they've given you to help you to do that.
So sometimes you've got to make sure that you turn over the page.
Make sure you turn over the page.
And read the full question before you go, how on earth do you convert from, like, you know, this crazy unit? Okay, so that really helps.
Yes.
Okay.
And so here I've written down those 4 equations that they've given you there.
Yeah.
Again, even though they've kind of listed the equations here, even though they, for example, said the values in the preamble, just writing it down in your own working as well can help you to refer back to them quickly. often it's better to write too much than too little, so you may as well if you've got the time. So they've given you these helpful formulae. Otherwise, we would think, how are we going to convert spectral flux density to absolute magnitude? But we've got these formulae, we're going to look at them here, and we're looking for one that relates absolute magnitude and F lambda. I mean, we've got one that relates absolute magnitude with apparent magnitude. Okay, that's a start, but how do we find the apparent magnitude? Well, they've also given one that relates apparent magnitude to F nu, which, well, what's F nu?
Yeah.
But then we look a bit further, and they've also given us a formula that relates F nu to F lambda. And we think, oh, that's what we've just measured from the graph. Again, this could be a potential point of confusion. Be careful to look at these subscripts here. The difference between F nu and F lambda, you shouldn't be too worried about it when you're trying to plow through this question in Olympiad. They're effectively the same thing, but with different units, and you get different ones depending on whether you think of the spectrum as having wavelength on the x-axis or frequency on the x-axis. And this is simply a conversion between them. What we want to do is find the absolute magnitude of this galaxy from the spectral flux density that we've just measured. And looking at these equations we've been given, we can see that we can use these three equations in steps to link up F lambda, which is what we've measured from the spectrum, with capital M, which is the absolute magnitude. So you can either do each thing in turn, find F nu, find lowercase m, and write out your intermediate values, which in a sense is good because the markers can check your intermediate values. But generally, we would recommend that you sort of manipulate everything algebraically and then put in your values at the end. It will be much quicker, I think, to do it that way.
And you've done it.
And you'll still get marks for your algebraic intermediate answers. And we have done this. Hang on. So we want an equation for capital M in terms of F lambda, because F lambda is what we've measured. So first, I've rearranged the first equation we were given for capital M in terms of lowercase m, and then things that we know. We've been given the luminosity distance, we've been given the redshift, so we don't need to worry about those for now. What we're worried about right now is what's lowercase m, the apparent magnitude. And then we look at the next equation we got given, and we say, oh, okay, this is linked to F nu. And also this third equation here links F nu to F lambda. So first we're going to substitute in this equation here, and we've got capital M, and we've substituted in this expression for lowercase m, the apparent magnitude, and we've got capital M in terms of F nu and things that we know. But we don't know F nu. So moving on, like I said, this is a three-stage process. We know that F nu is this factor times the wavelength squared times F lambda. And so we're going to substitute that in, and then finally, we've got this mighty expression for the absolute magnitude in terms of the wavelength, which, by the way, read these things carefully.
Oh yeah, it says.
We'll go through that in a second. We've got the absolute magnitude in terms of the observed wavelength, the spectral flux density that we've measured from the graph, the luminosity distance, and the redshift. And we know all those things, or we have just measured them, so that's great. But beware, they've given you these equations. Don't assume that anything has to be in a specific unit. Think about it, make sure everything's in the right units. They've also, this is a little bit sneaky, because here, the equation has been given with the symbol lambda without a subscript that denotes whether it's the emitted wavelength or the observed wavelength that you need to use in this equation. But then here they've said where lambda is the observed wavelength in nanometers. So yes, make sure to sort of look at these things carefully. When I've substituted in, I've written explicitly lambda subscript obs, just so I don't forget that this lambda here is the observed wavelength, not the emitted wavelength. Substituting the values in. You could simplify this before substituting in values, but honestly, it's quicker if you just put everything in my opinion. And you won't be as likely to make a mistake that you might make whilst sort of simplifying things and trying to make it more compact. And so we get that the absolute magnitude is minus 21.5.
Which is kind of what you're expecting, isn't it? Because you have to show it's between minus 22 and minus 21. So
we're happy.
Yeah, so I think it's always nice
Yeah.
when the answer you get is kind of where you expect it to be, and
Yeah.
that gives you a bit of confidence. And I
Yeah.
suspect you might be needing to use the answer later on. Often that's what you find with a show me question.
Yeah.
So the first part was done all right. And I guess even if you didn't quite get to the final bit, maybe you couldn't quite get the final answer, you just still got many marks from like showing you're working out in the kind of the intermediate steps.
Exactly. Something I said to the recently selected international team before they went into their team selection tests was, do the questions you can do, and then go to the questions you can't do. And if you can't do a question, do it anyway. And I think sometimes that's the mentality you need.
Yeah.
Like, sometimes you'll read it and you'll think, I can't do it, but then you just do it anyway. You know? It's the resilience. I think, honestly, to an extent, Olympiads are testing your character just as much as they're testing your skill.
Yeah.
If you're willing to really persevere and really just try and like extract marks from seemingly sort of a really uncrackable question,
Yeah.
we're testing that. Like, they're testing that just as much as sort of, do you know the equations?
Yeah.
I think this is one of those questions.
And it's
tests
definitely a
your
tough
character.
one. And it's not like lots of people are getting 100% is it on the actual test. So
Definitely.
I think everybody's doing hard questions and they're going to be hard and challenging and interesting for everybody. Right then, part B.
So we've done part A and we figured out that the absolute magnitude of the galaxy is minus 21.5. Great, I've denoted that M subscript G here.
Yeah.
And it's good to use your subscripts to make sure everything's clear.
I guess there's a lot of G's and M's and these kind of questions, aren't there, and L's and D's and things. So yeah.
Especially like once you've done part A, there aren't really any other absolute magnitudes it could be. But when you get to part B, suddenly we've also got we've suddenly got the absolute magnitude of the sun entering the chart. So
Here we go. Right. So
yes. So as I've said a few times, the first thing you do, you read the question and you write down the values that are going to be useful to you so that you can refer to them quickly later. So we've been told the absolute magnitude of the sun, so I've written that down here. And we've also been told to assume that all the photons being emitted are monochromatic with emitted wavelength 150 nanometers. And even though they've mentioned the whole 150 nanometers thing, this is still kind of new information in a sense. So I've written it down again. So we're assuming that all the photons emitted from the galaxy are all the same color, all the same wavelength, and they're all 150 nanometers when they're being emitted. And I've also written down clearly the value that we've obtained in the previous part, just so everything's clear so that we can refer back to it quickly later, so you're not kind of going through your earlier working, looking for values you might need. And so once we've done that, we ask, what's the question asking us to do? What's the instruction here? And the instruction here is to determine the SFR of the galaxy. And from reading the preamble, the SFR is the star formation rate. And you think, again, without these extra formulae, you might not know what to do. But we have these formulae that we've been given, and they've told you that this is how you work out the star formation rate of the galaxy. They've given you this formula, it's all handy, all's well and good, but they've done it in terms of N-ion. So we know how to find the star formation rate of the galaxy from N-ion. But what's N-ion? They've told you that. N-ion is the number of ionizing photons emitted per second by the galaxy. In general, if they say something slightly confusing, just go for what the most sort of simple, reasonable assumption would be. What I've decided is that the number of ionizing photons emitted per second by the galaxy is just the number of photons emitted per second by the galaxy.
Yeah.
That would make sense. Don't let extra little words throw you like that.
Cool.
Right, so N-ion, number of photons emitted per second. So what we're going to do to find the number of photons emitted per second, we're going to consider the luminosity of the galaxy, which is the total energy of all the photons being emitted by the galaxy per second. And we're going to divide that by the energy each photon has. And why have we thought to do this? Well, we know that the energy of a photon is, if I can just adjust this real quick,
Yep.
the energy of a photon is given by this equation, which I assume you'll know from A level. E equals HF, or here we've denoted the frequency as nu rather than F. You can use either. It's
confusingly looking like a V as well, isn't it?
It confusingly looks like a V. I've used nu as the frequency
because
they've used nu as the frequency in this question.
That makes sense.
To keep things consistent.
Yep.
Or equivalently, in terms of the wavelength, the energy of a photon is E equals hc over lambda. Energy in terms of wavelength is going to be more useful for this question because the reason we thought to use the energy of the photons in the first place was because they've given us the wavelength of these photons. They've said, assume that they all have emitted wavelength 150 nanometers, and that could be your first clue to know that you should use the energy that each photon has, because H and C are just constants. As soon as you know the wavelength, you know the energy that each photon has. But how are we going to know the luminosity of this galaxy? Well, we have its absolute magnitude, which, as you might know, as we mentioned, we discussed magnitude earlier on in this video. The absolute magnitude is a measure of how bright the object is at a distance of 10 parsecs. So the absolute magnitude is a measure of how intrinsically bright an object is, regardless of its distance. How much is it emitting? So we can use our formulae.
So we've got something over here, haven't we?
Yeah, we've got some formulae that might be useful here. Well, let's have a look. What's going to be useful? Here's the luminosity. We've got brightness in terms of luminosity, and we've also got magnitudes being related to brightness. So let's, as some of my lecturers would say, let's massage the equations for a minute. So what we want to find is the luminosity of the galaxy. What we know is the absolute magnitude of the galaxy, and in this question we've been told the absolute magnitude of the sun, which should be a clue that we might want to use that too.
Yeah.
So let's write down these equations. So we want to use this formula where, for example, say M1 is the absolute magnitude of the galaxy and M0 is the absolute magnitude of the sun. So let's just put those things in. And we're going to denote the brightnesses BG and B sun. Remember this circle with the dot inside denotes the sun, and I'm using subscript G to denote the galaxy. Hang on, but these should be capital M's because we're doing the absolute magnitude. Remember, lowercase m denotes apparent magnitude, uppercase m denotes absolute magnitude. Okay, so we know these values here, and we know the brightness in terms of the luminosity. So let's have a think about what BG and B sun are. Because we're considering absolute magnitudes, not apparent magnitudes, the distances that we put in here are not going to be the actual distances of the sun and galaxy away. We are going to simply put in the value of 10 parsecs as the distance. That's the convenient thing about using absolute magnitudes. We don't need to worry about what the distance actually is. We've calibrated the magnitude as such to pretend that the object is 10 parsecs away. Just a little simplifying. We get to this value here, BG divided by B sun, is actually going to be the same as the ratio of the luminosities. At this point, I'm going to look back at the question and remind myself what we're actually doing.
So here we go. So
we want to determine the star formation rate. Okay, and we've been given it in terms of n ion. Again, it's good to do this kind of check-in with yourself, which is why I'm narrating this.
Yeah.
So we've been given SFR in terms of n ion, and n ion is the number of photons being emitted per second. What we're currently doing is finding the luminosity of the galaxy so that we can divide it by the energy of each photon to see how many photons are being emitted per second. We can rearrange this for the luminosity, and once we've done this, we can put in some values. But that said, we don't actually need to put in values yet because we're going to want to divide the luminosity of the galaxy by the energy of each photon. There are a couple of advantages for substituting in things as you go. For example, the markers can check your intermediate values, and you can also do a gut check on your intermediate values to check that it's reasonable. But I don't really have an intuitive sense for how many photons a galaxy emits per second, so I wouldn't really be able to do a gut check on that fairly quickly anyway.
Even the magnitude of that, it's like, you could be so far off,
it's going to be so big.
Yeah.
Okay, we've been given a formula for SFR, star formation rate. Wonderful. And so let's just, now we can plug in the values because I mean, that's on camera. So before we've been told in this question that that's the star formation rate. We just multiply this value for n ion by this prefactor here, which is a very small number.
Yeah.
So let's work that out now. I'm going to put the numbers in straight away, I think. And if you plug that into your calculator, you get 97.7415 something, never mind. But what's the units of that? Because when you give an answer, you're going to want to give your units as well. So let's quickly look back at where this was given to us. And it says the SFR in units of m-sun per year can be calculated as. So we know our units now. So the answer, it's good to get in the habit of writing out your answer, separate line, slightly away from everything else so that it can be quickly seen.
So that's 97.7 solar masses of stars produced every year, is that right?
Seems like it. From looking at the units, you can kind of interpret what it means. So yeah, that sounds about right.
Cool, okay, so I've got nothing to really judge that number against, but it sounds about right.
Yeah.
And yeah, I reckon, well, it is the correct answer. But I think that, again, it's very nice to sort of see the way that you've laid it out. So you've written down the formulas that have been given to you, and it's just that kind of step-by-step logical approach of just trying to find out one more bit of information in each step that
when
you've got.
in doubt, write more, not less. Because if you write more, then that's more that can be marked.
That's true, okay.
You're more likely to get marks if you write more.
And the last bit then, it's just 1 mark, isn't it?
Let's
so the
do it
very
down
last
here,
question of this is about the age of the universe.
So the mass of the galaxy is about 10 billion solar masses. That's kind of awesome.
Yeah, yeah.
Assuming a constant star formation rate, estimate an age for the galaxy. Well, this is quite nice. We know that there's about 98 solar masses of stars being formed per year. We know that it's about 1 billion solar masses in its mass. So what we want to do is we want to divide that billion by this approximately 100. I mean, it says estimate, so I'm happy to round this to 100 for the purposes of this calculation. So we get age is about 1 billion divided by 100, which is 10 to the 7. And if we're writing this out, that's about 10 million. And this is really good because they've said, given the universe is 430 million years old at this redshift, is this age possible? And it is, because 10 million years is quite a bit less than 430 million years. So there's been plenty of time for this galaxy to get born, evolve, exist. This is good. So the answer to that last part is yes, this age is possible.
So that last bit there, actually not a lot of work for that last mark, so it's quite a nice finish. And I would say that this is a long answer question. I mean, section C, it does say long answer, but it is important to realise that you only have to do one of the 2 questions. So if people want to find out more or they want to have a go at this kind of question themselves, where can they go to find out more information?
Yeah, so head to the British Physics Olympiad website. Lots of tabs across the top. The past papers are available there, as well as the syllabus, which is a full checklist of things that you might get asked about, and the study guides that we mentioned in this video.
One of which you wrote.
One of which I wrote, one of which Alex wrote.
But they are really good, actually. And I think the important thing about this part of the Olympiad in particular is that you can learn a lot of it yourself and do a lot of self-study and self-practice. So if this is the kind of thing that you're interested in, then there's no limits to what you can actually do in terms of teaching yourself material.
Yeah, definitely.
But yeah,
just be courageous and resilient, because like I said, Olympiads can test your character as well as just your ability to sort of know things and remember things.
Yeah.
That's part of what it's about. It's not being scared.
Fantastic. Well, thank you so much for going through that today, and I really appreciate you taking the time to do that.
Thanks so much for having me here. It's been awesome.
Thank you. Cheers.